Hello and welcome back to another lecture from organic chemistry. In this lecture, we're going to go through the second type of a pericyclic reaction, and it will be the electrocyclic reaction. In electrocyclic reaction, we are taking a pi bond, turning it to sigma. So I'm going to say the delta H for this reaction, it will be negative or exothermic because we are taking a weak bond like pi and we turn it to a sigma, which is way more stable than pi. So the reaction is going to release energy. Now, if you want to take a sigma and turn it to a pi bond, that's gonna ask for energy, and in this case, the delta H of this reaction is gonna be positive, and we call it endothermic. Now, I have a molecule, and as you see, it has two pi bonds and two methyl groups that they are in the same direction. So I'm gonna say those methyl are in a cis configuration related to each other. And if I apply heat, I can break the sigma bond, and I'm talking about this sigma bond. I can break it and turn it to like a pi bond. And now from two, we got three of them. Okay. When I'm applying heat, the two methyl groups that will be outside of the molecule, far from each other. But if I apply light, one of them is inside, while the second is outside. And now I want you to follow this. So we know in order to break a sigma, we need to apply pi bond. And now when we are taking pi and turn it to sigma, still we need to apply energy, but the energy we are applying light instead of heat. The question is, why do I apply, how come we are not applying heat again and we are applying light? And the second thing is, how come we can start from two different molecules, two different isomers, and still get the same product? But this product is different than the starting compound. Question is, why? And what's the science behind it? Now, if I start with diene, do I get the same result? Looks yes. And again, we can use heat or light, and depends what we are using. We get different product. In one case, when we applied heat, and we turned like two pi bonds to one, and the two substituents, and now they are in the opposite direction of each other. I can use light this time instead of heat to break the molecule, or I can use light to run an electrocyclic reaction, but in this case, the two substituents will be in the same direction. So they will be cis, while here they were trans. Well, here, cis. Now, again, we are using different pathways to get same product. Again, same question. How come we are getting same product from different mechanism? And why do we get different, let's say, we can call them different product for the same chemical reaction? Why their configurations are different? Okay, let's tackle that one. We want to run electrocyclic reaction. An entire reaction is going to follow symmetry of the HOMO orbital. And remember, we are taking p orbital and we want to use them to turn them to sigma. So we need to be sure that that orbital, any p orbital that we are picking, and it has the same phase as the second one. When they are reaching each other, they're going to reach each other in a way to have head-to-head interaction. And if it's head-to-head interaction, we call it sigma interaction. So I'm going to rotate these two opposite of each other. For example, this one, it will go counterclockwise, while the left one, it will be clockwise, and now we will have interaction, and the blue is going to hit the blue, and I will get constructive interference, and I'm going to call it sigma bonding. Let's tackle this subject. Okay, and so we're going to pick some example. And the first example, we have trienes, and two methyl groups are opposite, they're outside of the molecule, and now this molecule, it has a 3 pi bond, so I'm going to say number of the HOMO orbital, it will be exactly equal to number of the pi orbital. Why? Because I'm using heat. So how about this? Make it as a note. If we are applying heat instead of light, the highest occupied molecular orbital, it will be equal to number of the pi bonds. Now, how many nodes I have? It will be n minus 1. And what's the n? The highest occupied orbital, which is the third one, minus 1. That's going to give us two nodes. Let's show the nodes. One node is going to be here, and that's going to be the second node. Okay, now I know node is going to change the phase. So how about this? Let's go with p orbital. I'm going to show the p orbitals. And I go, next step, I will give them sign, plus, plus, and then here, plus, plus, and that one will be up, plus, plus. And so as you see, I changed the phase whenever I hit the node. Okay, now I'm going to move them in a way that those yellow lobes are going to be facing each other. Okay, so here you go. We have the yellow lobes are facing to each other. I'm going to highlight them. Forgive me. Okay, now we managed to get sigma interaction between those two. So we got sigma. The question that I need to ask, okay, I need to answer maybe, and is what will happen to the methyl groups, and also what's going to be position of the new pi bonds or pi, or how should I rearrange them? Okay, and remember this pi bond is going to move here. That means this one is going to move there, and this one is going to move there. So from 3, I'm going to end with 2 pi bonds. So I'm going to show one here. The second one is going to be there. And I got 1 sigma. Now, if you move this one clockwise, the methyl group, it will go up. And in order, to bring the yellow facing to the second one, the rotation here is going to be counterclockwise. And if it's counterclockwise, then this one, the methyl group also, it will go up. So both of them, they went up, up. So my final product will be something like this. Okay. And I have two methyl groups that they are pointing same direction. So I'm going to show them same direction. Of course, I do have two double bonds here. And I'm going to say, this is my final product, CH3, CH3. Okay. Rotation here was, one of them was clockwise, while the second counterclockwise, and this one, it will be this rotatory. So if they are rotating opposite, it will be this rotatory. And remember this, that we started with 6, 3 pi bonds or 6 p orbitals. Now, let's repeat this one, but this time we are using, different isomer. The methyl groups, one is inside, one out. Again, we have two nodes. Let's show the nodes. One's here, second is there. Okay, so I'm going to say, okay. Next, I will say this one up, up, this one down, down, up, up. Okay, again, this one, it will move, let's say, counterclockwise, and this one is going to move counterclockwise. So I will get this. Then let's highlight them. Okay. If the left one is moving clockwise, the methyl will go up. And if the right side is moving counterclockwise, the methyl will go down. Okay. And we will have two double bonds there. So our final product is going to be something like this. And we have two double bonds. So 1, 2, and okay, next thing is one is pointing up, while the second one is pointing down. So what does it mean? It means we got position for the methyl groups. While the previous one, they were in a cis position or same direction. Now the rotation. Let's talk about the rotation. Okay, the rotation. The left one counterclockwise, clockwise, and the right one is counterclockwise. So rotation still is opposite, and I'm going to call it this rotator. Okay, and I'm using 6 pi bond p orbital, which is equal to 3 pi bonds. Let's extend this one to different number of pi bonds. This time I have 2. I'm using heat. So I'm going to say the HOMO is going to be equal to a second orbital. So I'm going to say electrons will be the second level of energy. So I go level of energy, which is n minus number of minus 1. That's going to give me 1 node. So I have only 1 node. Let's show the node. Node, I'm going to show it here. I have only 1 node. What does it mean? It means this. It means this orbital, okay? This orbit, the one on the left, let's say it has this color. Whenever we technically reach the node, the sign will flip, and this one goes down. And now we have orange, and any color that you see, and is going to be pointing down. Now I want to move them in a way to get this interaction. Okay. So let's say we want to move them in a way that these two are facing to each other. Okay. So how do we do it? Let's move this one. Let's move this one clockwise. And how about this? This one also, if I move it clockwise, then this one is going to go up. So the rotation, it will be same direction. Both of them are clockwise. And I'm going to say the rotation, it will be same direction. We call it conrotator. And what will happen with the double bonds? Okay, one of the double bond will move here, and that double bond is going to move there. So we're going to get a new double bond, and it will be this position. Okay, so here you go. New double bond is there. Now, how about the methyl? This methyl is rotating clockwise, so it will go up. How about the methyl on the left is, again, if we rotate them this one in this direction, methyl will go down. So I'm going to have one methyl up, and the second methyl is pointing down. So they will be in trans position. Now, if I take one of the methyl and bring it, closer to the second one, I'm talking about this. If I put it here and repeat the, like the experiment, and see what will happen. Okay, in this case, I'm pretty sure we're gonna have again the same product. It's just technically this is gonna show up here, and it will be, pointing to us. But let's repeat this one. Okay, so this time methyls are facing to each other, like close to each other, and so I'm gonna say again, I do have one nodes there. I go this one, it will be plus here. Let me draw the orbitals. Okay, this one it will be plus, plus, and then down plus, plus. Okay, let's rotate them clockwise, clockwise. Okay, and in order to get something like this. Okay, so the double bond, this double bond is going to shift here. Well, that one is going to go there, so we get double bond here. And now I will have these two orbitals are facing to each other. So I go, yellow is facing to another yellow one. And how about the methyl? The one on the left, because we are rotating it clockwise, it will go down. And the one on the right side, it will go up. Okay, remember, you are turning it clockwise. Right now, methyl is pointing, left, and when you rotate it, it will go up. And so this methyl, it will go up, and the one on the left, it will go down. Well, we have a double bond there. Now, let's compare it with the previous one. This methyl on the right side was pointing down. Okay, methyl on the right side was pointing down. Now is pointing up. And because this molecule, it has a symmetry, like it has the axis rotation, I can actually rotate the molecule in this direction here. Aligned with technically the Z, I can rotate it, and those two methyls, they turn to each other, and they will be identical. So I got the same product. Okay, let me summarize whatever I said until now. Now, if we have now 6 pi electrons or 3 double bonds, rotation, it will be this rotatory. And if we are dealing with 4 pi bonds or so 4 pi electrons or 2, okay, 2 double bonds, and the first one was 3 double bonds. And for dealing with 2 double bonds, rotation will be counter-rotatory. So counter-rotatory for for 2 double bonds, and this rotatory, it will be for 3 double bonds. And whatever we got until now in the presence of heat. Now, question is, what will happen if we switch to light instead of heat? The product will be different, and that's going to be a good subject, but for another lecture. And for now, thank you very much.